So welcome to the lecture number 3 of this course. In the previous lecture we discussed about space lattice and we understood what is 2D and 3D space lattice. We also discussed about crystalline and non-crystalline material. We understood that the repetitive arrangement of atoms defines crystalline arrangement, and if the atomic arrangement is not repetitive, it is random, then we will say that it is non-crystalline material. Then we also defined unit cell, and we have also discussed how to represent BCC, FCC and HCP, that is body centered cubic structure, face centered cubic structure and hexagonal close packed structure. Now let's start the discussion about some important terms related to the crystal structures. Let's discuss about coordination number. So the definition of coordination number is, it is number of atoms touching any one atom in crystal structure. Okay, so coordination number definition says it is number of atoms touching an atom in crystal structure. So from the definition we can understand that coordination number for BCC, FCC and HCP will be different because these are different crystal systems. The arrangement of the atoms are different in all these three structures. So coordination number for all these three will be different. Let's first see about BCC. Now in the previous lecture we represented the BCC unit cell like this. So as it is a cubic structure, this is a cubic unit cell, and we have atoms at each corner as well as we have one atom at the center. So this way we represented the BCC unit cell. Okay. This is called reduced sphere representation. Okay, but actually if we see, the atomic arrangement is such that these atoms are touching each other. So if I represent now full sphere representation rather than reduced sphere representation, I can draw the unit cell like this. And one atom will be behind this. So as you can see, this is the top face, this is the bottom face, and this is the atom which is at the body center. This is called full sphere representation. If we want to draw the unit cell for this full sphere representation, we can draw it like this. If we want to represent the cube, we can represent it like this. Okay, so we can see that we have atoms at each corner. So this is top face. We have atoms each corner of the bottom face as well. You can understand that one atom will be behind this, and this is the atom which is at the body center. Now for this representation, if we consider any one atom, let's say for this representation right now we are considering this atom, body center atom, then what will be the coordination number? So we can see that this atom is touching this particular atom, so it is also touching this, it will be also touching this. From the other side view, if we see, it will be also touching this. So there will be 1, 2, 3, 4 on the top face. Also it will be touching 1, 2, 3 and 4 on the bottom face. So actually this atom will be touching 8 atoms, right? So because of that, now therefore we can say that coordination number of BCC is equal to 8. Now for this discussion, I have assumed, or I have taken into consider the body centered atom. If we draw the full crystal structure with more atoms, and then if we consider any of the atom, let's say if we consider this atom or this atom or this atom, then also we will get the coordination number is 8. So this you can do in homework. You can draw the crystal structure of BCC like this, and then you can consider any one atom at any corner or at the body center, and then you can find out, and you will see that the coordination number will be 8 always, right? So similarly, now if we discuss about FCC, so how we represented FCC in the previous lecture? So we represented it by reduced sphere method, and it was like this. So we have atoms at each corner of this cubic unit cell, as well as we have atoms at center of all the faces. So this is top face center, this is bottom face center, this is left side face center, this is right side face center, this is front face center, this is back side face center. Okay, so this is the reduced sphere representation of FCC unit cell. But if we look at the full sphere representation, then we will be able to find out what is the coordination number of FCC. So let's take help of some computer figures, and let's understand this by PPT presentation.
If we look at the full sphere representation instead of reduced sphere representation of FCC unit cell, so it looks like this. So as you can see here, it is making a FCC unit cell, as this is one face having one atom at the face center, another face having one atom at the face center, and likewise. These are the corners 1, 2, 3 and 4. These are the corners on the top face. Similarly, we can see 1, 2, 3 and 4, fourth behind, corners of the bottom face. So if we consider the full sphere representation, then we can see that these atoms are touching each other. This atom is touching this, it is also touching this, it is also touching this, it is also touching this atom. So now if we want to find coordination number for FCC unit cell, we have to consider any one atom. So let's consider this particular atom, right? So now let's count this atom is touching how many atoms. So as we can see, this particular atom is touching 1, 2, 3 and 4, these 4 atoms, as well as this atom is touching this atom. So that means 1, 2, third on the bottom face and fourth on the right face, which is on the right of this if we look at it from this direction. So 4 more atoms, so that means 8. And now if we consider one more unit cell besides this, over here if we consider one more unit cell, then this atom will be touching face centered atom of that particular unit cell also, like it is touching over here. There will be one more atom over here, one at this face center, one at bottom face center, one on the right side of face center. So that means there will be 4 more atoms. So that makes 4 plus 4 8 and 4 more, so that is 12. So that's why coordination number of FCC unit cell is 12. Similarly, if we look at the full sphere representation of HCP unit cell, right? So this is the full cell representation of HCP unit cell. Okay, so as you can see, there are 3 atoms between these 2 layers. So this is the top face, this is the bottom face, and there are 3 atoms in between these 2. If we look at this unit cell from another direction, it looks like this. So now in this view it is clearly visible, 3 atoms inside this hexagonal cell. Okay, now if we want to find coordination number of HCP, this particular unit cell, then we have to consider any one atom. So let's consider this atom, which is at the face center of top face. So let's now count how many atoms are touching this particular atom. So let's see, this is 1, 2, 3, 4, 5 and 6. 6 atoms are touching. Then there are 3 more atoms which are touching this. So that is 1, 2 and 3. So that means 6 plus 3, it becomes 9. And then again if we consider one more such unit cell on top of this, so there will be 3 more atoms. So that is visible in this figure, right? So this is the unit cell which we have considered in the previous figure, and if we consider one more unit cell on top of it, then the face center atom which is on this face, that will be touching these 3 atoms as well, right? So that gives us 1, 2, 3, 4, 5, 6 plus 3 and plus 3. So that gives us coordination number 12.
Now the next term is atomic packing factor. The next term is atomic packing factor. Okay, so this is related to the how dense the atoms are arranged in any of the unit cell. Okay, and in short, the atomic packing factor is also called APF. So what is the definition of APF? APF is total sphere volume. That means over here we can read it as atoms, total atoms volume divided by total unit cell volume divided by total unit cell volume. Okay, so this is nothing but atomic packing factor. As I said, by APF we can think about how dense the atoms are arranged in particular unit cell. So we can find atomic packing factor for BCC, FCC and HCP, and okay, we will find it and we will see that which is the most dense structure, whether it is BCC, whether it is FCC or whether it is HCP. So by that we can also come to know what is the empty space in the unit cell, right? What is the amount of empty space available in any of the unit cell. So let's see how to find this atomic packing factor. So let's start with FCC. APF of FCC structure. Now for this, for calculating APF, we have to first find number of atoms per unit cell. Okay, so but now you can say that it is very easy to find number of atoms per unit cell. In case of BCC it is 8. Sorry, in case of BCC you may say that it is 9 because we have 8 atoms situated at the corners and 1 at the body center. Okay, but it is not that. While calculating number of atoms per unit cell, we have to consider sharing of atoms between unit cells. Like for example, if we have one unit cell like this, there must be another unit cell besides it like this. There must be one unit cell at the top, one unit cell over here, one unit cell at the bottom, one unit cell over here. Now if I say that this is one atom, but what portion of this atom is inside this unit cell? As this atom is shared by number of unit cells, I have to find that what is the portion of the atom inside this unit cell, right? So if we talk about FCC, okay, if we talk about FCC, then we can say that there are 4 atoms per unit cell. We have 4 atoms per unit cell. Now how it is 4? So let me draw a unit cell, FCC unit cell, by considering sharing of atoms. Okay, so we will have corner atom over here like this. I will explain why it is like this. We'll have one more corner atom like this. Let me draw it with different color so that we can have better representation. We have one atom over here like this, we have another atom over here, one atom over here like this, and we have face centered atom touching all this. Again we have one more face centered atom over here, and we have this atom over here, and this must be touching, this atom must touch this particular atom. Okay, we have one atom over here like this. Okay, then we have one atom arranged over here, and now we have one atom at the face center like this, and these two atoms are also touching each other. This atom is touching this. Now understand what this representation is. So as we can see, if we take neighbor unit cells over here, let's say we have this type of unit cell, so we will have one unit cell besides this over here, one unit cell at the top of it like this, one unit cell over here, one unit cell will be in front of this particular unit cell, one unit cell over here, one more unit cell at the top over here, one more unit cell over here. So this can be the arrangement. Now if we look at this particular atom is shared by how many unit cells? So we have 4 unit cells at the bottom and 4 unit cells at the top, and this particular unit is shared by all these unit cells. This particular atom is shared by all these unit cells, that means 8 unit cells. Now if we consider what is the portion of this atom in one unit cell, we can say it is 1 by 8. So that is why I have represented these atoms over here, and that is nothing but 1/8 of an atom. So if we take a sphere, if we represent the sphere like this, and then if we cut it in 8 parts, let's say I am cutting it from this, also I am cutting it from this, similarly I have one more cut over here and over here. Now if I represent one segment, this one segment, so that is nothing but what I have represented over here at all corners. So now we have 1 by 8th of the portion of atom at this corner. Similarly, at all the corners we have 1 by 8th portion of the atom. So we have 1 by 8 into how many? So 4 at the top face, 4 at the bottom face, we have total 8. Okay. Now plus, this is a face centered atom. Now if we again look at this arrangement, and if I consider a face centered atom over here, then this face centered atom is shared by 2 unit cells only. Okay, so we can say this is 1/2 of the atom. Similarly, this is also 1/2 of the atom, this is also 1/2 of the atom. We have one more atom on the left face, a half portion, one atom half portion on the back face, one atom half portion at the bottom face. So we have 1/2 into how many? So 1, 2, 3, 4, 5 and 6 faces, that means 1/2 into 6. So this gives us 1 plus 3, that is 4. So if we consider a single unit cell in FCC, we have 4 atoms only by considering sharing. So that way we can say number of atoms per unit cell in FCC is 4. Alright, so let's end this lecture over here. We will continue the calculation of APF of FCC in the next lecture.